Hello and welcome to Lesson 1 of Unit 8. This is statistical hypothesis testing. In this lesson we're going to be talking specifically about the student's t-test and also defining things about hypothesis testing. Okay. So just a quick example to kind of get us thinking about what hypothesis testing is. Let's say we know Frank, and Frank is a market gardener who grows tomatoes. Last year, Frank weighed a sample of 50 tomatoes and found that the mean weight was 106.3 grams with a standard deviation of 12.41 grams. This year, Frank used a new fertilizer to try to increase the weight of his crop. Frank collected a random sample of 65 tomatoes and found the mean weight of the sample to be 110.1 grams with a standard deviation of 31.1 grams. So some of the things that we might think about in this scenario is how could Frank use the information that he has to determine whether the new fertilizer was effective? What does effective mean? How significant is the evidence that Frank has in determining whether or not his fertilizer was more effective? What would it be more significant if the sample size was larger? So in this unit, we'll be talking about situations like these where we have sets of data and we want to compare the sets of data and ask questions like what's better, what's worse, is it just different? So in the past, we've often made claims about population parameters, such as the mean of a population or population proportion, otherwise known as probability. For example, a manufacturer of an insect repellent might make a claim that on average their new product is more effective than ours, and we call this a statistical hypothesis. What we'll talk about today is how we can start to test that statistical hypothesis. So there are three key components of hypothesis testing. First, we want to formulate some kind of hypothesis to test. Okay, this could include or should include a null hypothesis and some form of an alternate hypothesis. We should then calculate some statistics. So this today what we'll talk about is calculating a t-value, but there are other tests that can be done to calculate statistics to determine whether or not a hypothesis is true or false. And then we have to make some decision. So we have a hypothesis, we have calculated some statistics, and then based on the statistics we have calculated, we will then make a decision and conclusion about the population as a whole. So let's talk about hypotheses. Let's suppose a claim is made that a particular population mean has a value of mu naught. We call this the null hypothesis, or H naught, and we would write it as H naught is defined as mu equals the value of mu that we are claiming, mu naught. This statement we assume to be true unless we have significant evidence enough to reject it. If it's rejected, we accept that there is a difference between mu and mu naught, and this statement is called an alternative hypothesis, or H1. Some examples of what H1 could look like. So H1 could be the alternate hypothesis that the mean or population mean is actually greater than our claim or less than our claim. In both of those examples, we call those a one-tailed hypothesis, because we're testing one tail of the distribution curve. There's also the example that mu is just not equal to what we are claiming. This is called a two-tailed hypothesis. In this example, we don't really care if the mean is actually greater or less. We just care that it's different or not what the original claim was. So, going back to our insect repellent, let's say that we were a competitor who wants to have, or who is looking for evidence that the new product is actually inferior in protection time. So my hypotheses would look like, my null hypothesis is the claim that the protection time on average is 6 hours. The alternative hypothesis is that the actual protection time is less than 6 hours. If I am a market researcher studying all of the products on the market, I may want to just show whether or not the new product differs from the old one, but not necessarily be concerned with whether the protection time is greater than or less than the original. So these hypotheses would look something like this. So my null hypothesis stays the same. I'm making the claim that the mean protection time is 6 hours, and my alternative hypothesis is that it is not 6 hours. It's something different than 6 hours. Okay, so one more quick example about writing hypotheses in a different context. So here we are talking about submarines. So the top speed of submarines currently produced by a particular manufacturer is 26.3 knots. When their engineers modify the design to reduce drag, they believe that the maximum speed will be increased. So the set of hypotheses that I could use to test whether or not this statement is true, my null hypothesis would be that the mean speed of the new sub is the same as the old, right? 26.3. And I'm testing to see whether or not the mean is actually greater than. So my alternate hypothesis would be that the mean is 26 or is greater than 26.3. So, step 2, we have to calculate some statistics. So, just a quick interjection of a historical note. This is kind of an interesting story. There's a mathematician by the name of William Gossett who's employed by a company called Guinness to improve the taste and quality of their products. And in order to maintain the quality of the hops that were used in the brewing process, along with the help of another mathematician by the name of Carl Pearson, William Gossett developed a statistical test. Okay. The work that he and Carl Pearson put together was eventually published in a journal in 1908, but in an effort to protect the sort of the power of this test in comparing year to year or batch to batch products, William Gossett disguised his name and used a different name, Student. His concern was that other brewers would look at his name and his association with Guinness and then use his work to their advantage. So for this reason, we actually still today call this particular statistical test Student's t-test instead of Gossett's t-test. So what is Student's t-test? Well, first of all, it is a test statistic, or it gives me a test statistic. And what a test statistic is a value that summarizes the information in a sample. The t-test is specifically a test used for two data sets that are measuring the same thing. So for instance, submarines, right? I had an old set of submarines and a new set of submarines, but I'm measuring their speeds. This test only applies to normally distributed data. So this is what the test itself looks like. So we're considering some hypothesis test of the null hypothesis that mu is equal to mu naught, given a sample size of n with a sample mean of x bar and sample standard deviation of s. The test statistic is calculated as so. And what this test statistic is doing is it is giving a value that's standardizing the difference between the sample mean and the claim of the population mean. It's standardizing it through that division of the standard deviation and the square root of the sample size. As the sample size grows, this value should approach 0, since if I were to increase the size of my sample, I'm getting closer and closer to sampling the entirety of the population, in which case the sample mean becomes the population mean. Do remember that this only applies to normally distributed data, so that either has to be told to us in advance, or we have to be able to show in some way that the data is normally distributed. Okay, so let's talk about using this test statistic. Well, let's talk about calculating this test statistic. So going back to the example about repellent, let's say that manufacturer claims that their product lasts longer than 6 hours. An independent researcher takes a sample of 50 bottles of the new product and found that the mean protection time of those 50 bottles was 6.12 hours, with a standard deviation of 15 minutes, or a quarter of an hour. In this case, the test statistic would compute to about 3.39. Great. But what does this tell me about the claim? So in the next couple of slides, we're going to talk about how this value, this test statistic, is then used to calculate or produce some conclusion about my hypothesis. But some things to consider or think about while we were looking at the next couple of slides is, if a different random sample was taken, would we expect the new sample mean and standard deviation to be the same? What if we had collected many samples of 50? How might we be able to represent these samples? So let's talk about making decisions. So a couple of vocabulary words first. The p-value of a test statistic is the probability of that test result being observed if the null hypothesis is true. The significance level, alpha, of a statistical hypothesis test is the largest p-value that would result in rejecting the null hypothesis. Any p-value less than or equal to alpha results in rejecting the null hypothesis. And that is sort of the key part of this slide. Any value less than or equal to alpha results in rejecting the null hypothesis. So to those questions on the prior slide, if we continue to take larger and larger sample sizes, or just different samples, what we would end up with is what appears to be a normal distribution with mean 0 and standard deviation 1. But it's not quite normal. It's a little different. It's a little bit flatter than a normal distribution. And it's this red probability distribution that we will obtain our values of p, the probability that a test statistic is being observed. So if enough sample trials are taken, the resulting distribution is called a t-distribution, and that's the red graph. The black graph is a normal distribution, just for comparison's sake. So, going back to our insect repellent example, so far we have talked about a claim that the product lasts longer than 6 hours, and a researcher who's taken a sample of the product and calculated some statistics. So we have some hypotheses: a null hypothesis that the that the population's mean is 6 hours, and our alternate hypothesis, which is that the population mean is actually greater than 6 hours. We have calculated a test statistic from our sample size of 50, and now we can use our test statistic along with a significance level of 0.01 or 1% and determine Which of the hypotheses we should accept? As we are considering an alternate hypothesis that's one-tailed, i.e. that the population mean is greater than or less than, and in this case, greater than, the p-value that we'll be testing is the probability that the t-value the probability that a randomly selected t-value is greater than or equal to the t-value that we've calculated. So, just a note about the alpha value. This value can vary in its selection, and it depends on a lot of different factors. One of the main factors in considering the selection of an alpha value is the impact of rejecting the null hypothesis. So, for an example like this, where we're talking about insect repellent, the impact of rejecting the null hypothesis and accepting that the mean is greater than 6, or that the protection time is greater than 6, that impact could be fairly significant. It could lead to a market shift in which insect repellent is being purchased over others. And so we want this test to be fairly rigorous. Now, we won't encounter situations in exercises where we have to select a value of alpha and then justify it. We will, for the most part, be told what value that we should use for alpha for each problem. It'll usually be somewhere around 5% or 0.05. But it could be as small as 0.001 or a 0.1% significance level. Okay. So, with the significance level, our calculator not only can give us the value of t, but it will also give us the value of p, the probability. And again, this is the probability that a randomly selected t value from a sample size of 50 is greater than or equal to the t-value that we selected. And that's assuming that the null hypothesis is true. So think about it. That p-value is very, very low. So that is saying that there is actually a very low probability that that this should have occurred, assuming that the null hypothesis is true. So, because that p-value is less than our significance level, we can reject the null hypothesis, and therefore the new product does in fact last longer than 6 hours. Okay, so let's look at a summary of the steps for this process, and then we'll look at 2 more examples. So, state the null hypothesis and an alternative hypothesis. Step 1, got to have hypotheses to test. State the significance level alpha. It's really important that this is, whether this is given to you or if you're writing your IA, that you state a significance level prior to applying a test. Because what we don't want to do is select a significance level that gives us the result that we're looking for. Rather, we would like to determine a significance level, justify that significance level, and then determine through our test whether or not to accept or reject our hypothesis. Okay. This is one way where fishy statistics can be done in research, where a research team may perform their tests initially and then go back and determine their significance level so that they either can or can't reject their null hypothesis, giving a conclusion to their work that they were anticipating versus a conclusion that is probably more accurate. So, using the appropriate test in your calculator, we're going to calculate the values of t and p. The value of p is the value that we're going to be using for the most part. The value of t just comes with the territory. Using those values and our significance level, we will either reject or accept the null hypothesis. We will reject the null hypothesis if the value of p is less than alpha. We will never formally accept the null hypothesis. We will just not reject it. Okay? And then we will interpret our decision in the context of the problem. In other words, write your answer, your conclusion as a sentence. Okay, so let's look at some examples. This first one is about seafood wholesalers. Let's say that we're a restaurant manager who goes to a seafood wholesaler and inspects a large catch of 50,000 prawns. It's known that the population is normally distributed in terms of its weight. The restaurant manager will only buy the catch if the mean weight of the population of 50,000 prawns exceeds 55 grams per prawn. So I'm not going to weigh each prawn. That's a lot. But instead, what I could do is take a sample of prawns, weigh each of them, and consider the sample mean, standard deviation, and use a test to determine whether or not the population has a similar characteristic. So we'll take a random sample of 60 prawns, and we determine that the sample mean is 56.2 grams with a standard deviation of 4.2 grams. Then we're asked to calculate a one-tailed hypothesis test with significance level alpha is equal to 0.5 or 5% to determine whether the manager should purchase the catch. So, step one is to write our hypotheses. I like to define mu, what mu is talking about. In this case, mu is the population mean prawn weight. So my hypotheses, my null hypothesis, is that value of mu, the population mean, is 55 grams. The alternative hypothesis is that it is greater than 55 grams or exceeds 55 grams. Then I need to calculate a test statistic. So, as I've been saying, my calculator can do most of these steps for me. Oh, let me move my, let me move my face over here. There we go. So, on my calculator, I'm going to go to Stat, Tests, and then the second test is labeled the t-test. That's going to bring up a wizard, and there's a couple of things that I want to change in there. So the first one is that at the very top where it says input, I'm going to be inputting statistics. I've already calculated statistics for my sample. I'm not going to be inserting data, so I'm going to use the stats variable for input. The stats that I'm inputting were in the problem. My sample, my sample size n is 60. The value of mu, the population mean prawn weight, or mu, or mu naught, is 55 grams. The sample mean weight, or x bar, is 56.2 grams. S, the sample standard deviation, is 4.2 grams. The significance level doesn't get put into the calculator. It's just something that we consider. And then at the bottom, there are some options for choosing my alternative hypothesis. This alternative hypothesis is testing whether or not the sample population is greater than the claim of 55 grams. So we'll use greater than mu naught for mu. And then hit calculate. And what you'll see is that you're given a bunch of information, but the two values that we're going to be looking at are the t-value and the p-value. The t-value we'll look at and note, but we won't really use it very much. It's nice to note whether it's positive or negative, because that can tell me whether or not my sample mean is greater than or less than the population, and the value that we really want to use here is that p-value. So looking at the p-value and comparing it with alpha, we see that since the p-value is less than alpha, that is enough evidence to reject the null hypothesis, because the p-value, remember, represents a probability assuming the null hypothesis to be true. And since the probability is so low, we can say that there is statistical evidence to show that the null hypothesis is not true. And we then instead accept the alternative hypothesis. Okay? So thus the mean weight, we can say, exceeds 55 grams, and the manager in this case should purchase that catch. Okay. So last example, packing sugar. So we have a machine that packs sugar into 1 kilogram bags. It's known that the masses of these bags of sugar are normally distributed. A random sample of 8 filled bags was taken, and the masses of the bags measured to the nearest gram. Their masses in grams were as given. Okay. Perform a test at the 1% level to determine whether the machine underfills the bags. So first of all, mu is the population mean of the packs of sugar. The population mean of the sugar pack masses. Excuse me. My hypotheses are that the population mean is 1 kilogram, and the alternate hypothesis that I am looking at, is that that population mean is actually less than 1,000 grams. So to calculate these statistical tests, we actually have a little bit of extra work that we have to do. Because this time I wasn't given the statistics about my sample, instead I was just given the data of my sample, I need to insert that data into a list. So we'll stat, edit, and enter those values into list 1. Then we'll go back to stat, test, and then look at my t-test. And then instead of using the statistics or stats option for input, we're going to use data. When we use the data method for input, you'll see that it asks for a list. We're going to give it the list 1, or whatever list we chose to put our data in. We're going to use the value of 1 for frequency, because we're considering each of the values in my list once. And then my alternate hypothesis is slightly different this time. In this case, I'm looking to see whether or not the population mean is actually less than 1,000 grams. So I need to change that at the bottom where it says mu to less than mu naught, and then calculate. So we get my t-value and my p-value. We notice that the p-value is very high in this case, which says that assuming the null hypothesis is true, this value of t was very likely to occur. So because that value of p is less than the value of a, and by the way, this is the value of alpha, that 1% level language in the problem is referring to the value of alpha that I should be using, which is 0.01 or 1%. So because the value of p is greater than alpha, there's insufficient evidence to conclude that the machines are underfilling the bags. But that doesn't mean that I can assume that the machine is working properly. I cannot then say that, oh yeah, the machine is filling bags at an average mass of 1,000 grams. I just know that it's not less than 1,000 grams. It could be 1,000 grams, it could be more than 1,000 grams. So if I wanted to gather more information about what it was actually doing, I'd have to perform a different test. I mean, I could perform the same test. I could do a t-test, but I would have to change the way that my hypothesis is calculating. Okay, so that's all for the lesson. There is practice available on Schoology. This slide deck does have a video link to a YouTube video about how to use your calculator for doing t-tests. And then, of course, you can review this recording as much as you'd like. If you are in Ms. Thomas's class, you can ignore the due date for this practice. The due date for your practices is the class period after the lesson, the day that you're reviewing this lesson. Thank you, and have a good rest of your day.